Hello friends, today we will study hardening heat treatment. Hardening is a kind of heat treatment wherein castings are heated above upper critical temperature or sometimes above lower critical temperature, held for some time, followed by rapid cooling or quenching. So ultimately the process increases high hardness. There are some certain applications they require high tensile strength, high hardness, wear resistance and abrasion resistance so that the component may be successfully used for heavy duty purposes, and that property can be achieved by adopting a hardening heat treatment. Such properties are obtained by process called as hardening. However, increasing hardness also increases brittleness, that is embrittleness, the structure, and therefore hardened steels are subjected to post-tempering operation before any further use. The process consists of heating hypo-eutectored steels to above upper critical temperature, that is A3 temperature, and hyper-eutectored steels are heated above A1 temperature. Then they are held till complete austenitization is carried out or occurs, then followed by quenching in a suitable quenching media, where the quenching media is so used that which is allowing cooling more than critical cooling rate. The increase in mechanical property is due to formation of metastable phase, that is martensite. So austenite will directly transform into martensite, which is very hard and ultimately a brittle phase. So in case of hardening, austenite, which is showing FCC structure, will get directly transformed into a BCT structure, that is body centered tetragonal, and this body centered tetragonal kind of structure is observed in case of martensite. So it has a effect of carbon percentage also. Hardness value goes on increasing with increasing percentage of carbon. So low carbon steels are possessing low hardness, and till 0.8% carbon steel, as carbon percentage is increasing, hardness also goes on increasing. So hardness after hardening increases with percentage of carbon. This slide gives idea regarding what should be the hardening temperature for steels. So this red color zone indicates the heating temperature up to which castings should be heated for a complete austenitic structure, to form a complete austenitic structure. So till 0.8% carbon steel, these are hypo-eutectored steels. So for complete homogenization of austenitic structure, castings are heated well above A3 temperature. As in case of hypo-eutectored steel at room temperature, the phases observed are ferrite and pearlite. So that will be reducing hardness value at room temperature. But when the castings are heated above A3 temperature and then they are suddenly quenched, austenite will get directly transformed into martensite. This is in for case of a hypo-eutectored steel. But in case of hyper-eutectored steel, well below ACM temperature and A1 temperature, there is a presence of cementite, that is Fe3C. So ultimately cementite is also a hard phase. So to avoid unnecessarily heating, hyper-eutectored steels are normally heated above A1 temperature so as to save the energy cost or heating cost. So combination of cementite and martensite will ultimately increase the hardness. So hyper-eutectored steels are normally heated above only A1 temperature, but hypo-eutectored steels are normally heated above A3 temperature for carrying out a hardening heat treatment. In this slide, hardening heat treatment is shown on TTT curve, TTT diagram. There are two lines are shown here. One indicates surface layer and another indicates a core or central portion. So outer surface will directly come in contact with quenching media, and inner core will take some time so that hardening will occur at the central core area. So austenitic structure will directly transform into martensite. Martensite will start here and it will end here. So ultimately austenite will get directly transformed into martensite. As martensite is very hard phase, it will increase the brittleness also. So to restore that brittleness occurred because of hardening operation, hardened components are normally tempered. So tempering is carried out further. So tempering means it is a heat treatment where castings are heated with a temperature less than lower critical temperature. So that temperature may be in the range of 200 to 300 depending upon what kind of tempering treatment is there, whether it is a low temperature tempering, medium temperature tempering or high temperature tempering. So in case of tempering, castings are heated below lower critical temperature, then they are held for some time and they are followed by slow cooling. So because of slow cooling, again that brittleness is restored and component becomes somewhat tough. That is called as a combination of hardening followed by a tempering operation. So quenching is one important step in carrying out a hardening process. Quenching process for hardening of different steels. So quenching media plays an important role in getting ultimately mechanical properties. So proper quenching media should be used such that the component gets cooled at rate just exceeding the critical cooling rate of that steel. So if castings are cooled above the critical cooling rate, then only hardness is going to be increased. Otherwise there will be presence of some percentage of retained austenite that will ultimately reduce the hardness, and the purpose of increasing hardness will not be achieved. So always in carrying out heat treatment, your rate of cooling should be more than critical cooling rate. Then medium carbon steels have higher critical cooling rate and hence water or brine quenching is necessary. In case of high carbon and low alloy steels, they have slightly lower critical cooling rate because addition of higher carbon percentage and addition of some low alloy steels, the TTT curve will be shifting towards right hand side. So ultimately that will be reducing the cooling rate. Has to be hardened by oil quenching. So water quenching shows very high cooling rate than a oil quenching media. Then high alloy steels have lesser critical cooling rate as compared to medium carbon steel and low alloy steels. Hence some of the alloy steels can be hardened by simple air cooling, because in case of high alloy steels their TTT diagram will be shifting more towards right hand side than in case of a medium carbon steel or plain carbon steel or a low alloy steels. As here three different TTT diagrams are shown, and here it is shown that what is the effect of alloying element on critical cooling rates. So alloying element shifts TTT diagram to the right hand side, therefore increasing the hardenability, that is ability of getting hardened, and that will be allowed with oil or air hardening. So this figure will indicate hardening of a alloy steel. So you can observe here the rate of critical cooling rate is very less as compared to a plain carbon steel. In case of a plain carbon steel, the critical cooling rate is here. Critical cooling rate means it is a rate of cooling rate which will be suppressing per lead transformation. So among plain carbon steel, 0.8% carbon steel has the highest hardenability. Then in case of decreasing percentage of carbon, TTT diagram will be shifting towards left hand side. So you can observe difference between this figure and this figure. So it is more and more difficult to harden the steel. That is why low carbon steels cannot be hardened by water quenching. They require a surface treatments for getting hardened. So they are needing faster and faster cooling rate as critical cooling rate is increasing. So practically it is not possible to achieve such kind of cooling rates. So TTT diagram for 0.3% carbon steel. Here the nose of C-shape curve, instead of S it is C. It is touching the y-axis. The critical cooling rate is almost a vertical line, meaning steel has to be cooled at cooling rate equivalent to infinite, which is practically impossible. Therefore, we say that mild steel cannot be hardened by regular water quenching treatment. Then there are some factors that are affecting hardening process or hardness property, that is chemical composition of steel, that should be homogeneous. So low carbon steels cannot be hardened by regular oil or water quenching. Size and shape of steel parts, very bulky components cannot be hardened throughout. So sharp edges, sudden change in dimension should be avoided. Hardening cycle, that is heating followed by cooling. Temperature, soaking period is also an important factor. Homogeneity and grain size of austenite is also one factor. Homogeneous austenite with appropriate grain size will give better hardening properties. Quenching media should be used such that its rate of cooling will be more than critical cooling rate. Then surface conditions of steel, the steel part should be free from oil, grease or any other foreign particles like dust and oxide layers. Internal stresses present in steel should be less, that is casting should be free from internal stresses. This figure indicates a conventional kind of hardening where castings or samples are heated to austenizing temperature and they are rapidly quenched in a oil quenching or water quenching bath. Then they are followed by tempering operation. So it is a single media quenching media where continuously it is cooled from austenizing temperature to well below the martensitic finish temperature. As in case of conventional hardening, practically it is not possible to get a very high critical cooling rate. So to avoid that, quenching is carried out in two different medias. Firstly, the specimen is water quenched up to this portion, then the sample is taken out from water quenching bath, then it is cooled in a oil quenching bath. So it will reduce the critical cooling rate. So a stepped quenching is carried out. So initially faster cooling to avoid the nose of TTT diagram. This is the primary requirement so that to achieve high hardness, followed by slow cooling in a second quenching media. So it will ultimately reduce the critical cooling rate, and such kind of quenching is practically it is possible. Then by using spray quenching, the first figure indicates a casting with a complete austenitic structure, that is before quenching. Then the component is subjected to water quenching, water spraying, that will increase the outer surface to be getting hardened. So after quenching, the outer surface will become very hard, and depending upon hardenability of steel, we will get a varying hardening inside the core also. So that again depends upon hardenability of that steel. Hardenability is ability of steel to be getting hardened up to certain depth. Then quenching with self-tempering kind of treatment. Castings are heated up to austenizing temperature, then they are suddenly quenched in a oil quenching or water quenching bath. Then that same sample is again taken out from water quenching bath, then it is allowed to cool naturally for some time period. Then again that sample is immersed in oil quenching bath or water quenching bath, then it is taken out from water quenching bath again and it is kept for cooling for some period. So step by step cooling and removing the specimen is carried out, so that step quenching is carried out here. So it is a kind of a self-tempering, slightly slow cooling, then again quenching. So alternate quenching and holding outside for temperature to equalize. So such kind of treatment will increase the hardness also, and slightly tempered brittleness can be also improved.